Sorry?
The buttons.
Sorry?
Buttons.
I think around there, but I could be wrong. All right, people, we should make a start. So, lots of housekeeping stuff. Quiz 2 due late tomorrow night. We're going to miss a seminar on Friday. I will just record one and put it up on Echo 360. Up to you if you want to watch that the moment it comes out or a week later or whatever, sometime between then and our first seminar back after the break. If you're missing an applied class on Friday, you'll get the participation credit automatically, but we're also running a bunch of online makeup classes. You're welcome to attend one of those. I think there are 3 that we have listed. I think one is this afternoon, one is today, one is tomorrow, and one is the day after that. I forget the exact timings, but they're up on Moodle under week 5. All the usual stuff. Solutions to assignment 1 will be out late tonight. Assignment 2 is now available, but you have until after the break to worry about that. And keep an eye on your applied class participation marks. You can see them on Moodle under grades, at least you should be able to. If there's any problems with that, see your TA in your next applied class. Okay, so this week we're going to be talking about functions. And you've probably seen a bunch of functions in the maths you've done, which is good, right? It means you know something about this, which is good. But be a little bit careful. We're probably going to be looking at functions sort of in a more formal and more general way than you've possibly seen before. So a little bit of a warning is sort of don't assume that you already know everything we're about to do, because you might, but you might not as well. As one little example, you know, if you you think every function you can tell whether it's one-to-one based on a horizontal line test. I have some bad news for you. That's not going to be true for our functions, right? So, yeah, just keep an eye on this stuff. Okay, why might a computer scientist care about functions? So, firstly, it's just a bit like how I said with sets, that when people write about maths or computer science, they use sets a lot. Same is true with functions, right? You know, it's just part of the language. It's important to be able to speak it. But for our definition, fairly general definition of a function, you know, there's a reason that subroutines in a bunch of programming languages are called functions, right? They are very closely related to the functions we're going to introduce here in the mathematical sense. In fact, if you think about functional programming language paradigms, so there's probably newer ones around, but Lisp, Pascal, Rust more recently, functions in those are really exactly functions in the mathematical sense. And they're used to define a whole bunch of other important concepts. So that's my pitch for functions. Okay, so this is going to be partly a recap of what you might have seen in the video, but it's important stuff, so let me go over it one more time. So, think of a function as a black box, but a black box with two colourful labels on it, right? So, we first are going to have a label which is going to correspond to inputs, right? These are the things you are allowed to feed into the function, allowed to feed into the black box. And then there's going to be another colourful label which is sort of, it's a guarantee that everything that comes out of the box will be amongst the things on this label. Right? So if this label says integers, it's a guarantee that everything that comes out of the box is going to be an integer, but it doesn't mean that necessarily every single integer can come out of the box, right? Maybe -7 can't. So if you've programmed in typed languages, for example, this second language is second label is a bit like a return type, right? We're just guaranteeing that what we get back is going to be one of these things. And the key property of a function, and I'll say this 16 times during this lecture, is that for every input you get exactly one output, and it's the same output every time, right? There's no randomness, there's no anything else. So each input produces exactly one output. In particular, each input does produce an output. There's no such thing as putting something in the box and not getting anything out. And it's always the same output for a given input. So that's the concept. That's the concept behind what a function is. So for example, we could have inputs positive integers, outputs positive, allowed outputs positive integers, and our function could square things, right? That would be a legitimate function. You put in 2, you get out 4, and so on and so on. Okay, so how are we going to make this a more formal mathematical thing rather than a box? Well, the first thing is, as I said when we were talking about sets, mathematicians are bandits for expressing everything in terms of sets. So our domain is going to be a set of things, which are our allowed inputs. Our codomain is going to be a set of things, and that's a guarantee that everything that comes out will be in that second set. And then we could sort of think of this box as just all the input and output pairs, right? Or in this case, a table of inputs and outputs. You input x1, you get out y1. You input x2, you get out y2, etc., where all the x's make up this set and all the y's are in this set, but they don't necessarily make it up, right? Might be some things in this set which are not in this whatever. But again, a table, not quite a formal mathematical object, so what do mathematicians do? They make another set. But this time they make a set of ordered pairs, right? So input, output, input, output, input, output, right? So the function formally is three things. It's a domain X, it's a codomain Y, and then it's a bunch of ordered pairs from Cartesian product of X and Y. So first things in the ordered pair are in X, second things in the ordered pair are in Y, with the special property that there's exactly one ordered pair XY for every X in X, right? So what does that condition mean? Someone, why is that condition there, that there's one ordered pair for each X in X? Yes, exactly. Every input has one output, right? So for everything in my domain, I do see an ordered pair and I have an output, but also I only see one, right? Because if I had like, 1, 6, and also 1, 7, I wouldn't know what the function output, right? So it needs to be exactly one. So that is the crucial property of a function. For every input, there is exactly one predetermined output. Okay. So remember that for us, the domain and the codomain are part of the function. They always need to be defined. It's not a function without a domain and a codomain. So in this case, this is a codomain to some degree, all right? So, okay, this is what we've just said, I think, and the only extra thing there's a couple of extra things here. Let's talk about the extra things. So up here is what we've just said. Of course, if we have an ordered pair AB in the set which defines our function, then we write that f of A is B, right? That's our notation for when you input A, you get out B. F of A is B. Obviously, I think you've seen that before. Okay, so now, new definition. So the set of values, Y values, that actually occur in these pairs. So remember, the codomain was just a guarantee that all your outputs would be, say, integers or whatever. But the set of things that actually comes out of the function is called the image of the function. People sometimes also call it range. We'll call it image, right? So that will definitely be a subset of your codomain, but it may not be equal to the codomain, right? And in fact, there's a special word for when it is equal. When the image is equal to the codomain, that means that the function does actually output everything in its codomain on some input. We call that onto, right? There's an even fancier word for that, surjective, if you want to use a fancy word, but onto will be good enough for us. Okay. Any questions on all of that? We'll actually see, I know that was a lot of hand waving, we'll actually see some examples. So again, just to go through it, the function is a domain X, codomain Y, a set of ordered pairs from X cross Y, one for every X. The set of things that actually comes out of the function is called the image of the function. The image is always a subset of the codomain, but if they're equal, we say the function is onto. And very last thing, this is getting a tiny bit ahead of where we are in the notes, but because it's a pain to always say f is a function with domain x and codomain y, we use this as a shorthand, right? So again, we're double using this notation. It's not a logical notation anymore. This is saying f is a function with codomain x to codomain, with domain x to codomain y, right? Okay, so here is a function, f with codomain 0, 1, 2, 3, with domain 0, 1, 2, 3, codomain 0, 1, 2, 3, 4, 5, 6, defined by doubling. So that would be a table of values for this function. How would we write it as a set of ordered pairs? Like this, right? On input 0, it outputs 0. On input 1, it outputs 2. On input 2, it outputs 4. On input 3, it outputs 6. Now notice that there's another function with the same rule. This is also a doubling function, but it's a different function, right? If you change the domain and the codomain, you change the function, right? So this is a function from all the real numbers to all the real numbers defined by doubling. And here we can say, well, the set of ordered pairs that defines this almost feels like cheating, but is the set of all ordered pairs of a real number followed by twice that real number, right? And when you think about it, that set of pairs, if you drew that as a set of xy pairs, what you'd get back is the graph of the function, the plot of the function, right? So there's a sense in which that plot is really actually what defines the function, if you want to think of it like this. Incidentally, is this function onto? No, right? Because the image of this function is 0, 2, 4, 6, just these things, but there's more stuff in the codomain, right? So the 1 is in the codomain, but it's never actually spat out. So that means this is not onto. Is this function onto? Yeah, because you can, any real number will come up as double some other real number, right? So again, this hopefully convinces you these are two very different functions. This one not onto, this one onto. Okay. So one really useful way to view functions, at least for me, is to draw what we call an arrow diagram of them, right? So let's take that function we saw on the last slide. What we do to draw an arrow diagram is we put a dot on the left-hand side of our page for every element of the domain. There they are there. We put a dot on the right-hand side of our page for every element of our codomain, and then we join things by arrows, exactly joining and, drawing an arrow from the input to the associated output, right? So this is an arrow diagram of our doubling function, and now sort of visually, how can you tell? Well, okay, so firstly, visually, what is the image of this function? It's all the things on the right that have arrows pointing into them, right? So the image 0, 2, 4, 6, it's just all the stuff that has at least one arrow pointing into it, right? In this case, it's exactly, but even if something had, you know, 3 arrows pointing into it, still in the image. Of course, it's only in the image once because it's just a set. Great. And how can we tell that this is not onto? Because there's some things that on the right that don't have arrows coming into them, right? Yeah, no, okay, cool. Yeah, okay, great. So image 0246, not onto. Is this making some sense to everyone? Okay. So there's one question which is a good question which I get a bit when, at least in past years when I've taught this stuff, which is why not just always set your codomain equal to your image, right? Sort of, we basically get to choose our codomain. Why not always choose it to be the image? That seems a nice, simple choice. It'd simplify a whole bunch of stuff. And there's sort of a bunch of reasons why we don't do that, but let me give you one of them. So here's a function from the reals to the reals, right? F of x is x to the 8, 102x to the 7, minus 7x to the blah, 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 right? Now, I can look at that, and I can see that it's a completely legitimate function from the reals to the reals, right? It's a mess, but I know if I plug in a real number here, it's going to spit me out a real number. It's all fine, right? But, so we've set the codomain to be the reals. It's fine, makes sense. But what's the image of this thing? I don't know. I don't want to work it out, right? It's probably an enormous mess. Maybe it's not. I didn't check. But sometimes actually pinning down exactly what the image of a function is super difficult. And it's much nicer to just be able to say, okay, the outputs will be reals. That's all we really care about here, right? And then there's sort of also a perhaps more philosophical reason for this, which is sometimes we really do want to think of functions as maps from a certain set to a certain set in particular ways, and that sometimes it's intuitively useful to think about that. So for example, the functions that map reals to reals make a nice class to consider without sort of subdividing them according to exactly what their images are. So there's various good reasons why you want to keep your codomain and your image as separate concepts, if that makes sense. Okay, so name me some ordered pairs, input-output ordered pairs of this function. 0, 0 is one of them. 1, 1, 2, 4, 3, 9. Agreed? Right. Okay. So, let's do something. And check with the person next to you, even if you're fairly confident you know the answer. How are we doing? Another 30 seconds. Okay, so I do agree with the majority of you here, but it really is important that we get this across. So there are enough people wrong to make me feel all right about trying to explain this fairly carefully. So remember, the key property of a function is that every input needs to give exactly one output, right? We're defining this as input-output pairs. Now here, this tells me 0 maps to 7 and 2 maps to pi, but this is meant to be a function I can enter 0, 1, or 2 into. And this one does not tell me where 1 goes, right? So what happens when I put 1 into the box? Box doesn't know what to do, nothing comes out, or it blows up or something. It's not a function, right? T is fine, right? When I put in 0, I get out 7. When I put in 1, I get out 1. When I put in 2, I get out pi. Completely legitimate function, that's fine. U has its own problem, right? And that is when I put in 0, I get out 7. When I put in 1, I get out 4. So far, so good. But now when I put in 2, it seems to say I get out pi, but then it also says when I put in 2, I get out 3, right? A function should only have one output for every input. So this definitely not a function. Does that make some sense? Okay. So that is important stuff. T's fine. Okay. So the notes goes through a bunch of functions you're doubtless familiar with. So we could have a squaring function from the reals to the reals. Here's the set of ordered pairs. Here's that set of ordered pairs drawn, the plot of the function. The image of this is the set of all non-negative reals, right? We can't get negative numbers out, but we can get any other number out, because if you want a proof that you can get out a non-negative number y, the proof is when you feed in square root of y, you get out y, right? So speaking of square roots, we can define a square root function from the non-negative reals to the reals, like this. Plot looks something like this. And the image of this function, again, would be the set of non-negative real numbers, right? Because we're always going to get out a non-negative real, and we could get out any non-negative real number. So, of course, we could have chosen this codomain here to be equal to our image. In this case, the set of non-negative reals. That would have been completely fine. Then it would be an onto function, right? If it's your function, you get to pick the codomain, right? Last one, I think. We can also have a cube function. So here, reals to reals. In this case, this is, our image is the whole of the reals, right? You can get any number when you cube a number. And so this is an onto function as defined, right? Okay. So question 13.1 says, which of these rules give us functions? So, we're now going beyond just you put in a number, you get out a number. This is an example where we put in a set of natural numbers and we get out the least member of S, least element of S. Who thinks this is a legitimate function? Who thinks it isn't? Okay, I've got about 3 votes for yes and 1 vote for no, and on that basis, I think you're correct. I think this is completely legitimate, right? You input a set, that's still a single input, right? You know, it's just a set, it's a thing. Now, every set of natural numbers does have a smallest element, right? That was one of the key properties when we talked about induction or something, right? So if you put in the set that contains 2, 3, and 6, you're going to get out 2. If you put in the set that contains all the even integers greater than or equal to 8, you're going to get out 8, right? So legitimate function. I think that one's fine. What if we change this to, for each set of real numbers between 0 and 1, let g of x be the smallest thing in that set? Who thinks that's a legitimate function? Who thinks not? I think not in this case, right? Because unlike the natural numbers, finding the least real number in a set is not always possible. So think about all the real numbers between 1/2 and 1, non-inclusive, right? Strictly between 1/2 and 1. What's the least element of this set? Right, you want to say 1/2, but you can't say 1/2 because 1/2 isn't in the set. Right, and if you say, well, it's 1/2 plus 0.00001, I say, no, it's not, because 1/2 plus 0.0000001 is also in the set, right? So here, this isn't a well-defined rule. There will be certain inputs where we're not sure what the output is, not a function, right? Okay, for each circle in the xy plane, let h of c, so where our inputs are now, so this is hopefully convincing you that the functions we're talking about can have more exciting inputs than just numbers. So where our input is a circle in the xy plane, let h of c be the minimum distance of the circle to the x-axis. Who thinks this is okay? Who thinks not? Okay, I think this is okay. The only sort of tricky thing is that obviously some of these circles will intersect the x-axis, but presumably for those the minimum distance is 0. And for the other circles, I mean, presumably you're defining a circle by its middle and its radius. And given the middle and the radius, you can pick out the minimum distance to the x-axis. I sort of think this one's okay. Okay, for a pair AB of sets of real numbers, let SAB be the smallest set which has both A and B as subsets. This is sort of an unfair question because smallest is not specific enough to really tell you whether this is well defined or not. But I think there's a reasonably decent interpretation of smallest here that would say, well, the smallest set that has both A and B as subsets is the union. Right, because for any set that has A and B as subsets, the union will be a subset of that set. So I think there's a reasonable interpretation under which this is a function on sets of real numbers that outputs the union of the two sets. So you feed in a pair of sets and the output is the union of the two. And similarly, this would be, I think, arguably the intersection of the pair of two sets, right? The largest set, which is a subset of both A and B, any set which is a subset of both A and B is going to be a subset of the intersection. So arguably the intersection is the largest of those. So slightly vague, but yeah. Again, part of the point being functions can be more complicated than just, you know, you feed in a number, you get out a number, right? Okay, so this you're already cool with. We did this miles before the notes did. When a function has domain A and codomain B, we write it like this. And to some extent, if you're building the function, you get to pick your domain and your codomain, right? Don't obviously have complete freedom because you can't, you know, pick a 1 on x function with 0 in its domain or something like that. But within the limits of the possible, you get to decide what these things are. Okay, so question 13.2 says, which of these can be defined on the entire real line so that the function values also linear? In other words, which can we define as functions with domain and codomain, both the reals? So x squared, can we define this as a function with domain and codomain, both the reals? Who thinks yes? Good, good. Okay, I agree. Of course, the image here is only non-negative reals, but that's fine. We can still set the codomain to be the reals. 1 on x, who thinks yes? Who thinks no? So no, I think, because there's trouble for x equals 0. But you could definitely define it on the reals minus the set containing 0, right? That's your only trouble, so that'd be fine. Log x, who thinks yes? Who thinks no? So I think no, right? You can't take logs of negative numbers. So that's going to cause you trouble. Square root x, who thinks yes? Who thinks no? Same trouble, right? Not defined for negative numbers. Cube root of x, who thinks yes? Yeah, so despite us not being able to do this for square root of x, you can take cube roots of negative numbers, right? So for this, we can define it on the whole lot. Okay. Okay, so this lecture is packed with stuff. So, in fact, we're now getting on to some stuff that is in the next video that I'm asking you to watch before the next seminar. So hopefully that will act as a recap of what we're going to do here. But that doesn't mean you don't have to pay attention now, you still do, right? So, last really big thing for this seminar is one-to-one functions, right? The super fancy word I mentioned that onto the super fancy word for that is surjective. The super fancy word for one-to-one is injective, right? Just so you know, but we'll call them one-to-one. So a function is one-to-one if for everything in the image, there is only one thing in the domain that maps onto that thing in the image, right? So the notes, I'll get to some more concrete examples in a second, but the notes say, for example, cube is one-to-one because for each real number, there's only one real number which cubes to give you that number, right? Whereas square is not, because if you think about 1, there are 2 numbers which square to give you 1, right? 1 and -1. So that is exactly the horizontal line test I mentioned at the beginning. But be a bit careful. This was talking about square the function from reals to reals. If we had defined square to be a function from non-negative reals to reals, then it would be 1-to-1, right? Because now we know our inputs are non-negative real numbers, and so there's only one of them which squares to give something. So again, if you change the domain and the codomain, you get a different function. It might have different properties. It might be different in terms of its 1-to-1 and onto-ness. So, is this function with this arrow diagram 1-to-1? Who thinks yes? Who thinks no? Okay, so people who are thinking no are probably thinking, oh, it's not 1-to-1 because of this y2. But that's not part of our definition of 1-to-1, right? Our definition of 1-to-1 just says that basically there's nothing on the right with 2 arrows going into it, right? So this one still is 1-to-1. It's 1-to-1, but this just tells you that it's not onto, right? So I've already told you a few fancy names. If a function is both 1-to-1 and onto, the fancy name for that is bijective. That's what you were thinking about, I think, those people who said this wasn't 1-to-1. It is 1-to-1, it's not bijective, right? It's not onto. Okay. Is this function 1-to-1? Who thinks yes? Who thinks no? What's the problem here? Yep, so there's 2 things that go to y3. And in fact, in my head, if you ask me what is a 1-to-1 function, what my brain does is it says it's one where this sort of thing doesn't happen, right? It's one where 2 things, you never have 2 things collide into one output, right? So this is exactly what a 1-to-1 function is not in my head. That makes some sense? Okay, so the notes gave one definition of 1-to-1, which was saying for everything in the image, there's exactly one thing in the domain which maps onto that thing in the image. There's another really useful way another useful definition, which is particularly useful when proving things are 1-to-1. I'm going to quote a colleague of mine who I thought gave a sensational description of this sort of definition. So what this is saying is that if you take 2 things, but those 2 things might be the same, and you say f of x1 is f of x2, then if the function is 1-to-1, that will mean definitely that x1 equals x2. So Norm Doe's sensational description of this is you wake up drunk in a forest and you see 2 trees, but you need to figure out whether those 2 trees are in fact one tree, right? And that's what you're thinking with x1 and x2 here, right? So you're saying, I've got 2 things, they might be the same, and in a 1-to-1 function, if their outputs are the same and you can show that that means they are actually the same, that's 1-to-1, right? So that's the way this definition works. You can hopefully convince yourself that it's the same as the previous definition we saw. So for example, if I take the function from the reals to the reals given by 6x plus 2, I can prove it's 1-to-1 by saying, well, if fx1 equals fx2, this is for all x1 and x2 real numbers, then these 2 things would be equal, so 6x1 would equal 6x2, so x1 would equal x2. But of course, you can't do this with every function, right? Because if we tried to do it with a function like x squared plus 1, it wouldn't be one-to-one, because if we put in -1 and 1, we get out 2, right? So to prove this, to prove a function is one-to-one, you do something like this. To prove a function is not one-to-one, you just need an example, right? You just need an example of two things that collide when you hit them with the function, right? And that's all that's needed to prove that. Okay, so to show a function is one-to-one, prove if, for any two things in its domain, if the output on those two things are equal, then the things must be equal. To show it's not one-to-one, find, and this is sort of our logic negation stuff, a case where you've got two different things with the same output. Okay, so is the function from z to z defined by f of x is x squared plus 1? Is this one-to-one? Who thinks yes? Who thinks no? Definitely no, right? Because, for example, 1 and -1, we both get the output too. Okay. Very quick flux question. Almost the last thing we're going to do. And I will so getting tangled up here. So we'll only take, this will be almost a lightning round. Remember to watch the domains and codomains, right? Okay. Okay. Got a bit of a mix of answers. So, here's some examples for f, right? So f of 0, the least even integer greater than 0 is 2. F of 1 is 2, f of 2 is 4, f of 3 is 4. We can see this is not one-to-one, right? We keep having two things colliding. So that's not one-to-one. G of 0, 37, G of 1, 50. So, G's looking a bit better, isn't it? So F definitely not one-to-one because, for example, F of 2 equals F of 3. Just pick one example, that's your proof it's not one-to-one. G is actually one-to-one. So very last thing in this lecture, I'm going to give you a quick proof of that. How do we prove this? Well, we say suppose x1 and x2 are the same when we hit them with G. We want to prove that x1 equals x2. The important thing here is that x1 and x2 are natural numbers, and we know that, right? So then applying the definition of g, we get this. Then subtracting 1, we get this. Now, at this point, if x1 and x2 were integers, we'd be stuck, right? Because we couldn't guarantee that the squares of two things being the same meant the things were the same. But here, we know x1 plus 6 and x2 plus 6 are both positive. So their squares being the same means they're the same. And we can get down to x1 equals x2. And that's our proof. So G is 1 to 1. Thank you, people. See you Thursday. Yeah. Yeah. Yeah.
So, like, should we do opposite? Like, the largest set should be, no, the largest set should be the union, which is like that's the union, and the smallest section.
So have a close read, but the thing was like the thing for union, for example, it said the smallest set which such that both A and B are subsets of it, right? So the thought is which is the smallest of all the things that contain
Did you see the race, bro? Yes, bro. Carlos for the win, bro. I love Carlos.
No, I don't think so.
Steering had some problem. Now, bro, his brakes. Breaks. He got locked, right? Yeah, something happened. But you know, bro, I'm a true fan. Okay? If I'm cheering for Lewis Hamilton, bro, I'll always be cheering for Lewis Hamilton. Someday, like, when Max is winning this.
Wait, just
Yeah.
hang on.
Hamilton to Ferrari.
Bro, you see how he was winning and he got a 1-2 at the end. And George Russell crashed at the end of the round.
Okay, let's talk outside. Yep.